Yes, Popin, I'll explain. Can you just wait for 3 more minutes? ये तो बढ़िया चल रहा है। Yes, Pawan. So I'll explain vectored interrupt. Okay. So see, previously, are you there?
Yes, sir.
Yeah. So since he has asked this question, can you explain vector interrupt, sir? So here the idea is, okay, previously there used to be two kinds of interrupts, okay, hardware and software. Okay. So hardware interrupts were very, very hardcore. So it was like trap interrupt, okay, or reset 7.5. So what they used to do, you had a specific subroutine located at some dedicated memory location where your interrupt will trigger the functionality. Okay, so whenever that interrupt comes, the hardware interrupt, it used to go to that specific subroutine. But in software interrupt, what used to happen is the software interrupt used to have another layer with which you can actually decide which software interrupt has come, and accordingly you call the interrupt service routine. Okay, so there was another layer. In vectored interrupt, what happens is they have combined these two. So right now you can put your code anywhere in the memory. You can put your interrupt service code anywhere in the memory. But what is important is whenever the specific interrupt comes, let's say a processor has got 32 interrupt pins, okay, and you have connected all the interrupt pins to some external sources. So whenever the specific interrupt comes, it automatically jumps to that specific service routine. So that's why it is called vectored. Okay, that whatever data comes, whatever interrupt comes, it goes through one network vectored interrupt component, I think. Yeah, so it goes through that module, and then that specific interrupt triggers the specific service routine. So that is called vectored interrupt. Is that okay? Anyone who did not understand? Okay, let me open some questions. Okay. What is ARM performance? See, ARM performance is the measure at which your CPU performs. Okay, so ARM is a code. Okay, ARM is a processor. So when you say ARM performance, it measures how much in what clock speed it runs and how much is the million instructions per second. So normally a processor is decided by MIPS, million instruction per second, or if it is a floating point processor, it is called floating point operations per second. So that way our performance is measured. So do you want to know something? I mean, is that your question or something else?
That is itself, sir.
Okay, okay. So maybe I'll share my screen, and then what you can do, you can you see my screen? Please let me know. Are you able to see my screen? Hello?
Yes, sir. Yes, sir.
Sorry?
Visible, sir.
Okay, okay. Yeah. So try answering the first question. Anyone?
System very low.
Is it only very loud?
All of the above.
Yes, all of the above. Yes, right. So VHDL, Verilog, and System Verilog, all three programs are used for any kind of HDL languages. Of course, nowadays System Verilog is much popular. Okay, so Verilog or System Verilog both are very popular right now nowadays, more than VHDL.
Which is important, sir.
Sorry.
And very low and creative. Which one is very important?
Right now, Verilog is
That's
very
one
important.
important.
Yeah, if you know Verilog, then most of the problems will get solved because System Verilog is more like Verilog. So Verilog and System Verilog both are very good. VHDL is a very old language, okay, but still it is used for writing HDL codes. But VHDL is a very old language. So can you answer question number 2?
Both A and B, sir.
Both A and B. Yes, right. Okay. If anyone is not able to answer, please stop me. Okay. If not saying not able to answer, if not able to understand, please do stop me and ask me. Which of the following in Verilog? Acha, question number 3. What are the basic levels of bodily in Verilog? And can anyone give me an example?
All of them.
All of the. Can you give me an example of structural Verilog? Okay, let me connect the pen. Okay, because then I can tell you. Yes, so you see, when you write a code, for example, in the way uh, assign, okay, or let me write in notepad. When you have a code like this, assign, okay, x equals to 2, okay, this is called data flow modeling. The same thing when you write it like always at star x equals to 2, this is called behavioral modeling, okay. And then when we have something like, let's say, and a b, okay, and let's say c, so you are specifically calling one AND gate, so this is called as structural modeling, okay. So keep these three modeling techniques in mind, they are very important, okay, and you will require this, okay, and learn Verilog, okay. So learn, I'm not sure whether sir has taught Verilog here, maybe sir has taught, but then what is important for you is to practice. So I would suggest, if you have some tools, model sim, go ahead and download, okay, model sim, and you will get a feel of all this structure or different types of modeling, okay. Question number 4.
Jet, sir.
What is x, by the way?
Undefined.
Hmm?
Z is in the undefined value. There is no any
Ambiguous value, sir.
Sorry. Correct. Yes. So, what are the major data types in Verilog?
Both A and B.
Sure.
Yes, sir.
Okay. But you see, in Verilog, there is nothing called net or variable, okay. So all these things are represented in terms of vars, reg, okay. So it is important to know this. There is nothing called net and variable in Verilog. Keep this thing in mind. Okay. So what is this unary operator in Verilog? Any idea?
D value. It's called the
Sorry?
not unary operator. It's called the
I'm not able to hear you. Can you speak a bit loudly?
Option B, sir.
Option B. B or D?
D, sir.
Okay, D. So can you give me an example of unary operation? What can be an example of a unary operation?
XOR operation is also a unary operation, sir.
Yes. So, and why XOR operations are used in unary? What is the application? For, yes, you are right. For parity bit generation. Okay. So let's say you have 101101 and you want to generate a parity bit. Okay. So if you XOR all the values, you will get one parity bit. Okay, it depends, it is odd parity or even parity, that is a different case, but then yeah, that is a different case, but you can generate a odd parity or even parity. So this is a very useful operation, okay, to generate one parity bit. Very useful operation. So question 7, what does this mean? Anyone? Question 7.
Hello.
Yeah, hello?
Option A, sir.
Option A. Yes. Anyone has any question?
Option A is correct.
Correct. Option A.
So the total
Yes.
4 bits.
Sorry?
The given is the LSD bit. So totally 4 bits of input. Totally 4 bits of input.
Yeah. Totally 4 bits of input. Yes, exactly.
0 is the LSD and then 3 is LSD.
Good. Very good. Very good. Yeah. So what is this? Question number 8. It is inter statement delay or intra statement delay?
Intra-statement, sir.
Okay. And what is the meaning of this, if someone can tell me?
Explain what is the difference between intra-statement and the intra-statement.
Can you speak a bit clearly? I'm not able to hear you.
Can you explain, sir, intra-statement?
Yes, I'll explain. Yes. So in intra statement, what happens is, let's say you give, I do it here. In intra statement, what happens is, let's say you have written
So it
A.
will calculate B plus C.
Sorry?
Sir, first you calculate B plus C. Then it will assign to the temporary variable. After 10 seconds, it will assign to the A variable.
Okay, very good. And what about this intra? What is about this inter? So this is what? Inter or intra? This is inter. Okay.
Inter, sir.
Then you have #10 B plus C. So this is intra. Okay. So see, what happens here is, first your delay is performed. Okay. Then your B and C is updated. Okay. And then it is assigned to A. But in intra statement, first B and C is calculated, and after 10 units it is assigned to A. So this is intra statement. Okay, so first you calculate here B and C. Okay, then you have #10. Okay, then you have the delay, and then you assign it to A. Okay. But in your inter statement, it is B and C. First you wait, then you calculate B and C and assign it to A. Okay. So this is the difference between inter and intra. Now it is very important to know the differences between the two, and what exactly most of the time you require this inter statement delay. Okay, most of the time you require inter statement delay. This is much more important than intra. This is not that important. This is very important. Okay, most of the time, and you use this in test benches. Never use this in design. Never use this in design. Okay, always use in test bench. Very important. ठीक है. What is time scale 1 nanosecond and 10 picosecond? It is again one very important, directive. Time scale. Can anyone tell me what is time scale 1 nanosecond by 10 picosecond mean? Anyone? Am I audible? Am I audible?
Yes, sir.
Okay. So, for example, let's say if you are not able to answer, just tell me that you don't know. It is okay. I also don't know many things. So, or shall I explain this 9? Or instead of saying you don't know, you say, okay, you explain. So shall I explain question number 9?
Yes, sir. Explain it, sir.
Okay. See, in Verilog, what happens is, let's say you want to have delays, right? Let's say you are generating a clock. The precision of this clock, what is meant by precision? Precision is the least amount of change that you can bring into your clock. This precision is 10 picoseconds. So you can give, when you write, let's say 1.23, it will consider 1 nanosecond and 23 picoseconds. But if you write 1.235, actually what it means is 1 nanosecond and 235 picoseconds. But it will not consider 235, it will consider 223 only, okay, or 24, okay, because 5 is in between. So what it means is this 5 picosecond has been absorbed. Why? Because you have not defined the time scale directive precision as 1 picosecond. You have defined it as 10 picoseconds. And what is the step? The integer is 1 nanosecond. Okay. So whenever you have some values, let's say 2.35, you say it is 2 nanosecond and 35 picoseconds. Sorry, 350 picoseconds. So that is the meaning of time directive. It is a very important directive, and you should know this. Okay? So what it means is, let's say the unit of time in simulation is in 1 nanosecond. Okay? So you write 23.45, so it means this much nanosecond. Okay? And the value of time precision is 10 picoseconds. So you cannot write 453 because 453 would require 1 picosecond resolution. You can write only 45. So this is what is called as time scale directive. It is a very important directive, and it should be taken care as much as possible in the test bench. Yes, tell me.
So the answer is A and B, sir.
Sorry? Answer is A and B, yes. Okay. 10. Which one is 10? You see, equal to is used for what? Equal to is a blocking statement, okay? Equal to used in blocking statement. So a equals to 2. So you are assigning the value of 2 to a. Equal to is used in if else condition. If a equals to b, means whether if a is equals to b. But this equal to what it means is, see, right now the difference between equal to and equal to is 3 equal to's and 2 equal to is, here we will not be able to compare x and z. So for example, the value of a is 2 3x and the value of b is 2 3 2. Okay, you won't be able to compare. Okay, both of them will give same, the value is okay 1. But the moment you put equal to, it means that this value will also be, should also be x for the if else condition to turn out to true. Okay, so this is an important item in Verilog, and this one is not synthesizable. Most of the time this is not synthesizable. Of course, you have to know whether it is synthesizable or not from the synthesis document of the FPGA, but most of the time this is not synthesizable. It is only this which is synthesizable. So what will be the answer to compare x and z? The answer is C. Okay. Yeah. Nice. So what would be the output of this code? Can anyone tell me? Can please do this code and tell me? I'll give you 2 minutes.
Sir, is it 036?
Yeah, tell me.
036, sir.
036. Yes, and after that?
It will end, sir. Oh. It will disable the for out, sir.
Yeah, but after that what will happen?
After 6 it will add plus, sir. Then it will become 9. Then if 9 I equal to 9, it disables the for out, sir.
See, what will happen? You have this hash 5 finish, right? After this hash 5, you have this finish, right?
Yes, sir.
So 036 will happen. So after that, it will restart. So it will be 036, 036, like that. Okay. So 036, 036, 0. And what I would suggest is you try out all.
Yes, sir.
Huh? You try out all these things in a Verilog compiler. Okay, there are many online Verilog compilers, so please try out. I think that would be very, very nice if you can do. Okay.
Okay, sir.
Yeah. Because I can tell you this, but you will not feel it. So There are many things. For example, let's say there is something called, if you let's say yes, use this. This is very good. Okay, online Verilog compiler. If you start using this now, you will see there are many things which you are able to do. You can practice at the same time you can learn. Okay, so this online Verilog compiler is very important. If you have not taken a note, please take a note and check. Okay. Acha. How many of the following tasks are terminated by new lines? See this right, it is not terminated by a new line. Okay, just keep that thing in mind. So whenever you write something, you have to specifically mention a new line. Other things, display, monitor, strobe, they are all terminated by a new line. Okay, so this is a very important question for your exam. It might come. Yes. So let us go to, let's say, 4. Yeah, 4 I think I have already discussed last time. So maybe I'll skip 4. Okay. Let us discuss 5. Yes. So let us discuss 5. So are you aware of all these things, what is happening? Okay.
Yes, sir.
Yeah. So if you can tell me the first question, answer to the first question.
400 baud per second, sir.
Are you sure?
Yes, sir. Baud rate equal to bit rate by number of bits per second, sir. So by using that formula, we can get, sir.
So is it 200 or 400?
Sir.
Hmm?
No, sir. 200, sir. 200, sir.
Exactly, 200, yes. So it is
1600 divided by 8.
correct. Okay. So it is the bit rate, which is 1600 divided by 8. Okay. So this gives me 200. But why is this like this? Okay. So it is a 8-bit generator. Okay. So you have 8 bits getting generated at the same time. Okay. And this is at 1600 bits per second. Okay, so your 16 bits, so in the 1600 bits are getting generated per second. Okay, now 8 bits out of them, they are grouped because it is a 8-bit generator. So what is the number of signal changes? It is 1600 divided by 8. So always remember, okay, baud rate equal to bit rate divided by 8. Okay. Yeah. So can anyone tell me this one serial? But this is not that important. But if anyone knows it, they can tell me. So the answer is long. Okay. So just note this, because this is more of an information question. You need to be informed about this. You cannot apply your analysis on this. This is something that you should know. So just keep this in mind. Now this is another thing that you should know about the Arduino Uno chip. So how many timers it has? So again, this is the information question. So it is 2 timers. Okay. 2 8-bit and 1 16-bit. And I think you can concatenate this 2 8-bit also to make 1 16-bit. Okay. So keep this thing in mind. Okay. What is the temperature range of the LM35 sensor? Now you need to tell me this. You can search in the net and you can tell me.
-40 degrees.
How much? You can tell me by looking at the internet, but you need to tell me. Tell me what would be the answer?
-55 to 150, sir.
Very good.
The difference.
Very good. Very good. Yes. Okay. Keep these informations in mind. Okay. What are the types of memory found in Arduino Uno?
SRAM and PRAM, sir.
SRAM and
PROM, sir.
SRAM and PROM.
Yes, sir.
Are you
Sir,
sure?
flash SRAM and EEPROM.
I think it should be flash
Sir,
SRAM
option
and
C, sir.
correct. Option C. Okay. So can you tell me what is the difference? So flash is used for storing the main program, okay, and it is non-volatile. Oh, sorry, non-volatile. E2PROM is used for storing the boot code. Okay, and flash and SRAM is used for storing data. Okay, so keep these 3 differences in mind. Tell me 6. Anything? You can search in net also and tell me.
I don't know.
Both A and B, sir.
Both A and B. Correct, absolutely correct. Okay, both A and B. The question 7 is a bit tricky question. Okay, just read the question and then tell me the answer. If you are not able to understand, please tell me that yes, you have not understood the question. I'd be happy. Did you understand the questions first?
డిగ్రీ అంటే విచారించింది ఏం పైసలు
అది కొట్టిందా ఆ 100 రూపాయలే
నా దగ్గర ఏమంటారు
వాడు వేసిందంట నీకు
ఎప్పుడు తెస్తాను కదా
రైస్
Yes, anyone? So what it means is you have two processor, okay? Sorry. This is A and this is B. And let me write in one note. You have two processors, A and B. In A, what happens is the moment one interrupt comes, the automatic service routine is called. Now this does not require an intervention of the processor clock cycle, okay? Automatically it is called. In B, when the interrupt comes, it goes through a processing engine and then it is informed to CPU. So there is some loss of clock cycles, okay, here to do this operation. So that's why A will have more efficiency than B. So now this is the same as vectored interrupt, okay. This is same as this vectored interrupt, okay. So this is why A will have more efficiency than B, okay. Keep this thing in mind. Okay, which storage devices uses capacitors? Anyone? DRAM. Yes. So that's why in DRAM you also need a charging, discharging, refresh circuitry, okay. DRAM refresh rate. So because this DRAM uses capacitor, that's why it needs to be refreshed again and again and again, and that is the reason it requires a refreshing circuitry, which is a extra circuitry. So that's why you specifically need one DDR controller. Okay. And yes, this you should be able to tell me.
అలాగే 50 రూపీస్ ఉంది
యాభై మనీ ఉంటుంది అది అసలు
50 రూపీస్ వస్తుందో రాదో అని.
కంప్లీట్ చేసేదా
Popin, can you just mute yourself? Yeah. So what is the relation between power consumption and supply voltage?
Quadratic.
Why? Why? What will be the equation? But you see, normally when we write, just hold on. We write P equals to VI, na? Correct? So P is equals to voltage into current. So P is having a linear relationship with voltage. Why do we say quadratic? Why do we say quadratic? It is because I is dependent as V by R. So finally it is becomes V square by R. And R is a independent quantity. So when we try to find a relation between two variables, we need to make it, you need to make one variable, you have to express one variable in terms of the other variable and one independent variable. Okay. So I is not an independent variable. Okay. P equal to V square by R is an independent variable. So P is related to voltage by a quadratic equation. Okay. What are the number of IO pins in Arduino Uno board?
Yes, sir. 6.
Anyone else wants to answer?
6. The number of input pins in the Arduino.
You can search in the net and tell me.
Six.
Why do you say 6? It is not asking for analog IO pins. It has got digital also. So right now,
14.
very good, 14.
14.
Correct. Okay. Now, can you tell me this 500 and 2000? Can anyone tell me the answer?
Four, sir.
You are telling me,
4. 4, sir.
no, you are telling me the number of bits are 4, right? This is what you have calculated. Number of bits equal to 4.
Yes, sir.
Calculate the number of, but the question is calculate the number of signal units. So the number of signal units that can be calculated from the bit units is on the basis of 2 to the power 4. So answer is 16. So how do you find the number of bits? The number of bits is bit rate divided by baud rate. Four. Okay. And what is now this 4 is bits, number of bits. Okay. So number of signal units 2 to the power 4. 16. Answer is 16. What will be the output of the following piece of code? Can anyone tell me?
Eight, sir.
Very good. 8. So remember, char is 1 byte, short is 2 bytes. Okay. Long is 4 bytes. Float is 4 bytes. Okay. Wait. And your double is 8 bytes. Yeah. So maybe up till assignment 5 only we can do, because we can do assignment 6 maybe next time. So any questions you have? So I have finished discussing all the assignments. Do you have any question on the existing assignment, or any questions on the lectures? You can discuss with me. Any other questions you want to discuss?
Sir, please explain spatial versus dynamic supply voltage management, sir.
What is that? Tell me 1 second.
Spatial versus dynamic supply voltage, sir.
Spatial. Okay. Let me just find out what exactly what you mean. Can you tell me when sir has taught all this? I can look into the lecture and then find out. Are you looking?
Yes, sir, I'm looking. Sir, in power aware systems, sir is discussed, sir.
Power management. Huh?
Yes, sir, power aware system.
Oh, power aware system. So is it dynamic voltage management or dynamic voltage scaling?
No, sir. Sir is discussed like spatial versus dynamic supply voltage management, sir.
Spatial means this one, special.
No, sir. Spatial, sir.
Spatial.
Yes, sir.
Okay, and dynamic?
Supply voltage management.
Okay, got it. Okay. See what happens in this is in terms of all the ASICs that you make. Okay, so you're finally making one chip. So dynamic voltage management or scaling, what it means is, let's say that one unit is having, sometimes, let's say you are powering this with 3 volts, okay, and let's say this is working. Now 3 volts will also consume more power, right? But what you can do when you see that the power requirement is less, what you do is you bring down the voltage to 1.8. So this is dynamic voltage scaling. Okay. So when you bring down the power to 1.8, automatically this block consumes low power. Now spatial voltage. Okay. So in chip, what happens in IC, there are few areas which requires more power and there are few areas which requires low power. Okay. So this spatial voltage scaling, what it means, spatial voltage management, or what it means is you route the power or you route the voltage to this ASIC areas in a very dense way, okay, so that all the elements get the power. But here you do not need that kind of metal layers to generate the power, okay. So that is called a spatial and dynamic. So this is a very popular term which is used in ASIC. But can you tell me, is this the one you are looking for?
Yes, sir.
Okay. But maybe what I can do is I can follow the sir's lecture, and then next time when we are meeting on Tuesday, next Tuesday, okay. So when we meet on next Tuesday, we can discuss this. Who asked this question? What is your name?
Bhavya, sir.
Bhavya. Okay, fine. Because this, when you say a dynamic voltage management or dynamic voltage scaling, they are used for different purposes inside an ASIC. Okay, so don't go by the nomenclature, go by the concept. So maybe what I will do, I will study sir's lecture. Which lecture sir is covering on? He's covering in week 5 or week 4?
Week 5, sir.
Okay, fine. Week 5 in power level, right?
Yes, sir.
So yeah, I'll study and then I'll get back to you. It's Bhavya, right? I'll remember.
Okay, sir.
Yeah. You don't have an exam right now, na? You have assignment submission only on Wednesday, right?
Yes, sir.
Fine. So maybe I'll study that and I will tell you. Any other questions? Then in that case, let me see Bhavya's question only. Let's see this. In power, acha, week 5, right? Lecture 20. Let me.
This part is a very busy module and most this is a hotspot. Most of the
You see?
communications are being done here in the red one. So I want to make it faster. So I put it at 3.3 volt and 200 megahertz. Now, if I go from this sort of curve, I can say that at a particular frequency, at a particular VDD, what is the frequency that I can get. So here, here I can have at 3.3 volt, I can run it at 200 megahertz. Whereas this one is a standard one, not that busy. I run it at 1.8 volt, which allows me to run it at 100 megahertz. So I am slowing it down, I am reducing the VDD also, but I ultimately need to see, for most of the embedded systems, it can be a real time, there may be a real time constraint. So we have takes place. The analogy for this is the biological blood. Okay, you needed more power. Therefore, at suppose I had a level for every point. So, if and the cycle time there is 20. So the energy consumed is this. I will be getting from here. This is pertaining to this equation. If I go from this sort of curve, I can say that at a particular reducing the VDD also, but I ultimately need to see, for most of the embedded systems, it can be a real time, there may be a real time constraint. So we have to meet.
See, what it is saying is, okay, same thing. What I thought is correct, because there are many terms of them. So it is like you have dynamic voltage scaling, right? So dynamic voltage scaling means, for example, if this module is running at 3.3 and it is consuming more power, what you do, you dynamically change the voltage. It's 1.8. So what is the power of a embedded systems? It is C V square into F, right? So it is proportional to the square term of the voltage. Okay, so if you reduce the voltage by 2, the power will reduce by 4. Okay, so you have to understand that. So that's why this is called dynamic voltage scaling. Dynamic voltage scaling. Now what happens in your spatial part, some portions are running at very high frequency. Like I said, that this is a very dense network and it has got many functionality. Okay, so what you do, you increase the frequency of this and reduce the voltage of this. So your C V square F, C V square, if you reduce the voltage, the power will come down, but you can increase the frequency up to 4 times. If you reduce the voltage by 2, you can increase the frequency up to 4 times so as to maintain the power constant. Okay, if you have a very slow module, then what it means is, it will, for example, if you want to increase the performance of this, what you can do, you can increase the voltage here and maintain a less frequency. Okay, so that the power is uniform everywhere. So this is called spatial voltage management, and the first one is called dynamic voltage management. So is it clear?
Yes, sir. Yeah.
I'm not here. I mean, if you have any questions, you can tell. Yeah. Any other questions?
Sir, in the same lecture, sir is discussing on problems, sir.
In the
I
same
can't
slide?
understand the problem, sir. How that energy and
Can you tell me where? In which? At what time? This one?
Yes, sir, that one, sir.
Okay. Let me see.
For that, most of the systems that we have, we'll have some discrete levels of, say, maybe 3 levels of power supply. Okay? 3 levels of power supply, say 5 levels, whatever. So here we can switch between any of these levels and we can get the VDD. Okay? say it can be, this one is 5 volt, this one is 4 volt, and this one may be 2.5 volt. All right. So if we assume that sort of scenario, then let us assume this, that we are working in a scenario where VDD, I'll vary, there are 3 possible VDDs. One is 5 volt, 4.0 volt, and 2.5 volt. All these are volts. And once again, coming back to this here. So we are playing with the VDD, and depending on the VDD, we'll have some frequency component. And so consequently, we'll have the cycle time, and cycle time is the inverse, and we'll have the energy per cycle. Okay? So as you know that we can have, say at this, we have got 50, this is megahertz, I'm sorry. Frequencies in megahertz. So it can be 50, 40, and 25 megahertz. By the characteristics, I found that these are the values. So the energy per cycle, here we found is 40 nanojoule. For this, it is 25 nanojoule, and for this is 10 nanojoule. And the cycle time, therefore, this is 20, right, in nanosecond. Now, I am given a task. A task has, so my deadline is 25 seconds. So I am given a scenario where different, this is time in second. This is time in second, right? Now, if I have to run 10 to the power 9 cycles. So if I run it at 5 volt, say here it is, so this is 2.5 volt cycles, and I'm running it at 5 volt. So 20 nanoseconds per cycle. So it will be over by 20 seconds, right? Although my deadline was 25 seconds. So I have run it at 5 volt, and I could finish it off within this time. So the energy consumed is this, I'll be getting from here. So this is, the energy consumed is actually will come from, not from this is the task area. VDD taken 5 volt, I'll compute some energy here. How much will that be? Okay, 40 per cycle, and I took 10 to the power 9 cycles. So my energy consumption will be 10 to the power 9 cycles. Every time it is 40 nanojoule, right? Energy was in nanojoule. This was, I did not write. This was in nanojoule. I'm sorry, the energy given here is in nanojoule, so it will be 10 to the power minus 9. So that will be 40 joule. So I'm consuming 40 joule of power, 40 joule of energy by running it at 5 volt. But was it necessary? If I had, I mean, since I can run it at a frequency of 50 megahertz, I could finish it much earlier, which I need not do. If your constraint is that you have to finish the job as early as possible, in that case, certainly you can reduce it, right? But otherwise, I had the scope of reducing it. So let's try to do that. Hertz. 50 means 50 hertz. 5 volt means 50 hertz. So I have run actually 750 megacycles here. Cycle, right? Here we got seconds, right? What will be the energy consumption? Okay? Okay, stop here and we'll.
Okay, I got it. Yeah. So what sir is saying is, I'll put that in a different way. Okay. So what sir is saying is, you have an ASIC, you have a small chip. Okay. Now this chip can run at 5 volts, this chip can run at 4 volts, and this chip can run at 2.5 volts. Okay. Now when running at 5 volts, the cycle time can be 20 nanosecond. Okay. Let's see this. This is what he is saying. Yes, cycle time can be 20 nanosecond. And the energy per cycle is also given. Okay. So if you have this, you have 5 4 25 5 4 2.5, okay, 50 40 25, 50 40 25, 20 25 40. Okay, so what sir is saying is we can forget about this part, okay, that you can forget about this part. So at 5 volts you can run at the side, the frequency clock time period can be 20 nanoseconds. For 4 volts the clock time period can be 25 nanoseconds, and for 2.5 volts the clock period can be 40 nanoseconds. Okay, now you see the good part is that it is told that you have to finish a task in 25 seconds, okay, and that task requires 10 to the power 9 T cycles. Okay, so when I say T cycles, what it actually means is clock cycles. Okay, so 10 to the power 9 T cycles for with 20 nanosecond clock cycle will be 20 into 10 to the power 9. Okay, similarly, so when we run at 5 volts, the clock period can be 20 nanosecond, right? So if you tell that how much the task will take to complete, so it will, the task is given that the task will take 10 to the power 9 T cycles. Okay, so your task will have 10 to the power 9 into 20 nanosecond, so it will be 20 seconds. So your task will finish at 20 seconds, but given the deadline of your task is 25 seconds, so you are finishing the task ahead of time, much before the deadline. Okay, you still have 5 seconds buffer in your hand. Okay, now let's say that instead of doing like this, what if we take 4 volts? Okay, but we take 4 volts, at that time what will be the time required? Because at 4 volts the time T cycle is 25 nanoseconds, so it is 20 to the power 9 into 25 nanoseconds, which will be 25 seconds. So if you run the system at 4 volts instead of 5 volts, then you can finish the task just at the right time. Okay, but if you run your system at 2.5 volts, then you have 10 to the power 9 into 40 nanoseconds, means 40 seconds, which is which is beyond the deadline. So you cannot use 2.5 volts at all. Okay, but you can use 2.5 volts in combination with 5 volts, because you have still some buffer time. You still have some buffer time. So if you run your task in such a way such that up till T1 time it is at 5 volt, and up till 25 seconds it will be at 2.5. Okay, so if you run like that, what should be the answer? Up till T1 you are running at 10 to the power 9 into 20. Okay, 10 to the power 9 would say, let's say T1 cycles, right? So it is 25 seconds into 25 into 10 to the power 9. So you have some T1 which is running at 5 volts, and you have some 2.5 which is running at 2.5 volts. Okay, you see that the power that will be consumed will be as per this 25, right? 25 and 5 volts. Okay. So you do not run your 5 volts till the full time. Okay, you run your 5 volts till some time, and then what you do is you switch on your 2.5 volts. Now that will definitely reduce the clock speed, but still you had more time while you were using 5 volts, right? So you can adjust the time. So what sir is saying here is you adjust your time in such a way, you adjust your time, you see this one, that you up till for 5 volts you run up till 15. Okay, so if you see here, the task, you run 5 volts up till 15. Okay, and then you run at 2.5. So how will the calculation be? In 15 seconds how many cycles will get completed? 15 seconds divided by 10 to the power 9, right? So this will be the amount of cycles that will be required. So 10 to the power cycle plus you have this 10 cycles. Okay, this 10 cycles left, which you are doing again at 10 to the power 9. So total is 25 divided by 10 to the power 9, which means 25 nanoseconds. So this is exactly what you wanted. Okay? And you want to, if you multiply this 25 nanosecond with 10 to the power 9, then what will happen? You will get 25 seconds. So given the deadline 25 seconds, you can use your task, you can run your task for 5 volts up till 15 seconds, and then you can switch to 2.5 and run your task till the end of 25 seconds. So that way, if we calculate the energy, if you see the energy table that sir has 40, 25 and 10, right? So 5, 4, 2.5, 40, 25 and 10. Okay, so per nanosecond, this is joules per nanosecond or all those things. Okay? So you need how much time? This is 40 into 15 plus 10 into 10. Okay, so this much amount you need, whatever be the amount. Another way could be if you run the whole thing at 4 volts for 25. We have seen that within 20, if you run at 4 volts, you can complete your whole task in 25 seconds. So if you see the table is 25, right? So 25 into 25, okay, which is 625. See this number and see this number. So this is 600 and this is 100, so 700, right? So 625 is less than 700. So given the scenarios, you can run your task at 4 volts and complete within 25 seconds instead of running your task at 5 volts and then switching to 2.5 volts and then completing the whole task at 25 seconds. Okay, in both the cases your task will get complete, but what is important is which will take less power. That is more important. So is the whole exercise clear to you right now, the way we proceeded?
Yes, sir. Clear, sir.
Yeah. Any other questions? But there are several situations in real world where you need to switch power. Okay. So this example does not try to prove anything. This example is just a scenario where you can switch. If you keep your voltage constant to achieve one task, that will take less power than if you try to do the task by switching voltages. Okay, but there might be cases where switching the voltages will allow you to have the task finish within some time and still consume less power than having a steady voltage. Okay, so keep that thing in mind. So this is called this is same as your dynamic voltage management. Okay, keep this thing in mind, and this is very good for your embedded systems. So in embedded systems, you change your power to keep the embedded system alive for a long time. Any other questions? Anything else? Yes, so those who have questions, they can stay. The others, if you are done, you can leave the meeting.
Sir, what is nano programming and where we use it, sir?
Nano programming
Yes, sir.
or micro programming.
Nano programming, sir.
Okay. Just hold on. Oh, acha, that way. My nano programming is also called microcode. Okay. So, see what happens is, uh, uh, 8085, right? In 8085, you have many instructions in the memory. Let's say 3E, 4D, 5C, okay? But there has to be a code here. I mean, whenever you fetch the data, okay, this 3E has to be compared with some data, right? Has to be compared, has to be decoded to generate the next address signals, the control signals or the ALU signals, right? So this decoding is through a programming called nano programming. Okay, so what actually it means is basically what you are doing is you have nano programmed the decoder in such a way such that it recognizes only these instructions 3E, 4D, 5E. Okay, so these are that's nano programming is used in microcontrollers. Okay, so and this is also part of computer architecture. Okay, so there has to be someone, because see who is doing all this. So for example, who is storing this 3D, 4D, 5C, all this data? You are storing it. Okay, but then whenever you store it, whether it is a valid instruction or not, who will check that? So that is called as nano programming. Okay, so it is like an alternate way. So either what you can do is you can take this data, okay, you put in some digital logic and you generate a control signal. Another way is you nano program this data, a small control memory, okay, and based on this three, you compare this three with the available instructions here and you generate the control signals. Okay. So this is called as nano programming, and this is extensively used in microcontrollers and microprocessors.
Okay, sir.
Yeah. And the memory that is used is called nano control memory. So sir has taught all these things.
No, sir, he just introduced nano programming, sir.
Yeah. So this is stored in something which is called nano control memory. But I don't think right now these are being used much. This is what I feel.
Sir, what do you mean by heterogeneous registers, sir?
Okay. So there are two types of registers, no?
Yes, sir.
Yeah. So there are two types of register. One is homogeneous and one is heterogeneous. Okay. So can you tell me what is the meaning of this homogeneous register?
Sorry, I don't know, sir.
Okay. In homogeneous register, what it means is, for example, let's say what happens is in a microprocessor, okay, these are address, these are data, and they are all connected to some memory, okay, outside memory. But there are set of some registers, okay, which are packed and they form one set. So these are called homogeneous memory, homogeneous registers. But there are some registers which are scattered across. Here is one register, here is one register, and then so these are called heterogeneous register. Now, what is the advantage of heterogeneous register? The advantage of heterogeneous register is you do not need to have all the registers packed at one place, because that will simply use up your space. So you can scatter your register in such a way, see, let's say this is your processor code. If you scatter in register in this way, this is a heterogeneous arrangement. But if this is the code and you are making your register file in this way, this is called homogeneous. Okay? So this can sometimes lead to space issue. But this, it is scattered, but this is near the processor, so you will not have any timing issue. At the same time, you will have all the registers at your near the code. So this is called heterogeneous register. So these are called basically, which is scattered throughout the die of the processor. These are called heterogeneous register. Okay.
Sir, is there any examples for heterogeneous registers, sir?
Heterogeneous register examples are definitely there, but these are all, for example, let's say you have your ARM processor, right? You have your ARM processor. So you have this R0 to R16. So this is a set of homogeneous register, but there are some other registers, for example, the link register, okay, R50, R16, let's say 23. So they are all scattered across ARM, and they are called heterogeneous register. Okay.
Okay, sir.
Anything else? But if you want to study about this ARM processor registers. So there is set of register R0 to R15, I guess. Yeah. So this is in a single register file. Okay. So this is called homogeneous register. But there are some other register like the link register. Okay. The main stack pointer register. So these are all part of the heterogeneous register set. Anything else?
No, sir. Thank you, sir.
Good that you are studying. So you are in which year?
BTech third year, sir.
Okay. Which college?
Triple IT RK Valley, sir.
Okay. So how, right now you are being taught embedded systems, or how?
Embedded systems, sir.
No, you are learning from this NPTEL portal, or do you have something in your college also?
No, sir. Only from this portal, sir.
Okay, so I would suggest that, see, in embedded systems, since you are interested, there is something in ARM, right? So you have heard about ARM?
No, sir.
Okay, so ARM is a very, very popular processor. Okay, very, very popular processor, and it is very important also. So there is one NPTEL program in ARM. Okay, Introduction to Embedded Systems by Indranil Sengupta. I would show you.
Oh.
Yeah, this course. Please have a look. Okay, this is a very, very good course. I'm posting the link. This is a very, very good course. So, you should also study this along with this embedded system design. Okay, because this talks specifically about ARM, and this embedded system design takes care of everything.
Okay, sir.
So that way it is very good. Anything else? Any other questions if you have in mind?
No, sir. Thank you, sir.
Thank you. Aditya, Raja, Rahul Yadav, any questions? Okay, then I'll be there for 20 minutes more. If you are studying something, and if you have many more questions, then just let me know.
Sir,
Yes, please.
sir, many of them told that for embedded systems, Linux programming, C, C++, Python, these skills are required. Uh, Many of them told me that, sir.
So you require only C, okay? You do not require Linux. You require only C for embedded systems. In, for example, the online course that I gave, no,
Yes, sir.
and in there also it is only C.
Okay, sir.
So learn only C. What is your background? EC.
Yes, sir. Easy, sir.
Yeah. So you learn only C. That is more important. And I would suggest also to learn Verilog.
Okay, sir. Sir,
Yeah.
is Verilog also required, sir?
Verilog is required for embedded systems design. So in this course that you have, na, you require
Yes, sir.
systems design. Okay. So you require that. But you do not require Verilog as such for making embedded systems. For example, the link that I gave, which is for embedded systems design using uh, ARM. So there you do not require Verilog. You require only C. But
Oh,
if you design a whole embedded systems, and if you are having in any way any kind of FPGA, then you require.
okay, sir. Sir, suggest me some projects, like in embedded systems, which will have some great future, sir.
See, embedded systems, no, nothing like. The more you practice, the better it is. For example, if you have anything on, do you know C?
Yes, sir.
Okay, so if I ask you to write some motor controller, will you be able to do that?
Sir, what, sir?
Motor controller.
By specifying some voltage like that, sir.
Yeah, but how do you control it? Through a PWM, so pulse width modulation. So if you start your project with the small projects, now automatically you will learn to do some big projects.
Okay, sir.
Okay, so you can start with rotating a servo motor. Okay, you want to rotate a servo motor by 90 degrees.
Yes, sir.
Will be the embedded coding for that. So you can think of it like that, and you can start doing it.
Okay, sir.
That would be nice.
Okay, sir. Thank you, sir.
No problem. Good, you are taking interest. You should learn.
Okay, sir. I to take leave. Thank you, sir.
Sure, sure, sure. Okay.
Okay, sir.
महेंद्र, हाँ मैं जो है लास्ट फेज में हूँ, मे बी 5 minutes more. Yeah, okay. जस्ट खत्म हुआ. हाँ ठीक है, 2 मिनट.